This next lesson is on inverse functions, and again, the title may be misleading, making you think that it's all about algebra, but now we're going to give you some calculus tools that help you decide whether a function has an inverse or not, even in the cases where we may not be able to find the inverse. So this picture on the front page is a lovely picture. The green line is the line y equals x. The blue curve is g of x. The red curve is f of x. And if you remember from your algebra days that the inverse functions are reflections of each other across the line y equals x, then hopefully you can see that f and g are in fact inverses of each other. So let's recap some of the things that hopefully you remember from algebra. If f of x and f inverse are inverse functions, then f of x is 1 to 1, which means basically it passes the horizontal line test. That means that if I give you the y value on f of x, you can necessarily give me back the x value because there was only one x value that got me to that y value. If the point on f of x is AB, then I switch the coordinates and get a corresponding point on the curve f inverse. F of f inverse, the composition function, is the same as f inverse of f, and that gets me back to x. In other words, f and f inverse undo each other. And I'll put that in quotes just because that's not really very fancy mathematical wording, but colloquially it makes sense. The domain of f of x is the range of f inverse, and vice versa. The range of f of x is the domain of f inverse. Please note this huge warning. F inverse is not the reciprocal. So it's not the -1 power. The -1 there that looks to be in the same location as where an exponent would be, that's indicating the inverse of a function, not the reciprocal of a function. Let's look at these two functions just to remember. So this passes, y equals x cubed, passes the horizontal line test. So it has an inverse. Well, I should say at first, the preceding step should be it also passes the vertical line test, which means it's a function. So it's a function, it passes the vertical line test, indicating that it's a function. It passes a horizontal line test, indicating that it has an inverse, basically. And the inverse will look something like, well, if here's the line y equals x, then the inverse is going to look something like this. So this would be the graph y equals the cube root of x. And why do I know it's the cube root of x? Well, because what I know from algebra is that the cube root always undoes the cube. The real question then is, for the next graph, we see that it does not pass the horizontal line test. It does pass the vertical line test, so it is a function, but it doesn't pass the horizontal line test, which means it has no inverse. And what that means really is that there is no way to undo a square. But if I asked you, how do you undo a square, you'd probably tell me that you take the square root. Let's draw another graph. If we restrict, so let's say this is y equals x squared with x bigger than or equal to 0, so I have this restricted domain, then this graph passes the horizontal and vertical line tests. That's what I'm going to call the horizontal line test, HLT. So this one passes the horizontal line test, and in fact, the inverse graph would look something like this, and this is the graph of y equals the square root of x. Notice that y equals the square root of x has a domain of x greater than or equal to 0. It has a range of x greater than or equal to 0, just as the domain and range for y equals x squared if I only look at the right half of the curve. So that's just a little bit of review from algebra about inverse functions. Okay, so if we don't have a graph, then how can we algebraically test if a function has an inverse? Or analytically, maybe would be a better word there, because we might be using calculus. Theorem A says, if f is strictly monotonic on its domain, then f has an inverse. So monotonic, what does that mean? Monotonic means it's either always non-decreasing or always non-increasing. And you might be wondering how that's different than just increasing or decreasing. Well, non-decreasing means it could be increasing or flat, basically. So basically this means this is the same as saying if f prime of x is either always greater than or equal to 0, or if f prime of x is either always less than or equal to 0. Remember that a function is increasing or decreasing. Increasing means that it's, if I look at it from left to right, it has positive slope. Or decreasing means that if I look at it from left to right, it has negative slope. So again, the slope is talking about the derivative. So if the derivative is always positive, or at least non-negative, or if the derivative is always negative, or at least non-positive, then the function is monotonic, which means it passes the horizontal line test. So let's give you an example of maybe some function that we don't know about. So if I give you some function like this, you see that its slope is always either positive or in some places maybe 0, but it's definitely going to pass the horizontal line test. So that's what I want you to notice, is a monotonic function, either monotonically increasing or monotonically decreasing, it always passes the horizontal line test, and so it will have an inverse. In example 1, we're asking to show that this function has an inverse, but we've specified, don't even bother to find it. In fact, we can't find the inverse for this function. So note, there is no way to find the inverse. It's really common that we have functions that model life, for example, that we don't know how to find the inverse, but we can at least use calculus to prove that it has an inverse. So I'm going to take the derivative, which is fairly straightforward to do now that we know so much about taking derivatives. Okay, well this has only positive coefficients and all even-powered terms. And x to any even power is going to be positive. So this is strictly greater than 0 for all x. So even though I cannot find the inverse, I have just proven that the function has an inverse because its derivative is always positive. So this means that f inverse exists since f prime is always positive. So in other words, the function is always increasing everywhere. It's a continuous function. And if it's always increasing, that means it's going to pass the horizontal line test, which means the inverse exists. I can't find it, but we know it exists. Example 2, explore whether this function has an inverse. If not, can we restrict the domain so that it does? Well, let's start first with taking the derivative and see what the derivative tells us. So if we take the derivative, we get 2x. So you can see that this is greater than, if x is positive, then f prime, well, if x is non-negative, then f prime is non-negative. If x is negative, then f prime is negative. So basically, this function is neither monotonically increasing, so this function is not monotonic, which means f inverse does not exist. And I'm guessing that you knew this. I'm hoping, crossing my fingers, hoping that you knew this already from algebra, basically. If we look at what this function looks like, y equals x squared minus 4, it looks something like a parabola, like this, with the vertex at the point 0, negative 4. And it doesn't pass the horizontal line test. So we already knew going in, hopefully, from algebra, that this doesn't have an inverse. But now we just showed it with the derivative test. So the function is not monotonic. It does not have an inverse. But so how can we restrict the domain? So however, let's say this. If we have f of x equals x squared minus 4, where x is greater than or equal to 0, then f prime will always be positive on that interval. which means f inverse will exist. Well, we can also say that if we restrict the domain to be negative numbers for x, then the inverse will also exist, because the function then will be monotonically decreasing. And then if we can restrict the domain, which we did, find f inverse. Okay, if we restrict the domain in this fashion, then f inverse is going to be, the first thing we did to x was we squared it, and then we subtracted 4 from the square of x. When we do the inverse function, we need to undo things in the opposite order in which it was done. So we start with x. Subtracting 4 means adding 4, and undoing the square means the square root. And of course, undoing the square, getting the square root is only true because x is greater than or equal to 0. So let's check. Let's see what happens here. F inverse of f of x, that's x squared minus 4. If I plug x squared minus 4 in for x in the inverse function definition, I get x squared minus 4 all plus 4 underneath the square root. This gives me the square root of x squared, which typically would be the absolute value of x, but x is restricted. Therefore, it gives me x. So it checks that the inverse function that I proposed is in fact the inverse function. Example 3, find the inverse for this function and check your work. So basically this example is thrown in here for good measure, but this is really an algebra question. So let's go ahead and find the inverse with algebra techniques. And I'm not going to give a whole lecture about how to find the inverse. This is simply just a review exercise. So this is review exercise. If you need a lecture on inverse functions, you can go back to our 1010 or 1050 lectures. Both of them will have a lecture on inverse functions. So one thing we can do is switch the x and the y. A lot of people do that first, mostly because we're really attached psychologically to having the x as the independent variable. I'm going to specifically choose not to do that to test our psychological strength, I suppose. So I'm going to solve for x. I'm going to move everything around and solve for x. That's my goal. So I first multiply both sides by the denominator of 3 plus 5x. Now I'm going to multiply on the left the y through the parentheses. And remember that I'm trying to get x by itself. So I want to get all the non-x stuff on the left and all the x terms, or terms that include x in them, on the right. Okay? And on the right now, I want to factor out the x, because I'm trying to get x by itself. So now divide both sides by 2 minus 5y, and I get x by itself. This means that the inverse function of y is 3y plus 1 over 2 minus 5y. So let's call this f of x, just so that we have some function notation there. The inverse function of y is given by this function, but that means if I really want x as the independent variable, then just swap out x for y. It was just a name after all. So there's the inverse function that I'm proposing is true. Now we're going to check our work. So we want to check, this is what we're looking for, that f inverse of f of x gives me back x. Or f of f inverse of x gives me back x. So let's do f inverse of f of x. And I'm going to work from the inside out, although that's really a choice. I could also just as easily work from the outside in if you prefer. So f of x is 2x minus 1 over 3 plus 5x. I'm plugging that in for f of x, and now I'm going to plug all of that into my inverse function wherever I see x. So I get 3 times 2x minus 1 over 3 plus 5x plus 1, all over 2 minus 5 times this big lump. And now we have some things to do to simplify this algebraically. So I am going to choose, actually, let's erase those equal signs. I'm going to choose to multiply this by a form of 1, 3 plus 5x over 3 plus 5x. So I get 3 times 2x minus 1 plus 1 times 3 plus 5x. I'll write that out explicitly. All over 2 times 3 plus 5x minus 5 times 2x minus 1. Now collect like terms, multiply out and collect like terms. I get 6x minus 3 plus 3 plus 5x all over 6 plus 10x minus 10x plus 5. So the 3's add to 0 in the numerator, the 10x adds to 0 in the denominator. I get 11x over 11, which simplifies to be x. So it is true that the functions are inverses of each other. Just let me say a note here. Note. We should also check, if concerned, that the domain of f of x is the same as the range of f inverse, and vice versa. And domain of f inverse equals the range of f. I'm not going to go ahead and do this algebra step because this is just a review problem, but I want to make this warning just so that you remember algebraically that really we need to check that the two functions have matching domain and range, meaning that they're the opposites of one another. Let's talk about slopes of inverse functions now. So again, in general, you're going to be given functions for which we cannot find the inverse function, unlike the last example, but we can at least prove with the derivative that the inverse function exists, even if we can't find it. And in those cases where we cannot find the inverse function, it's still true that we can find its derivative at given points. And it's a pretty cool, powerful trick here. So I'm going to take this point here, and I'm going to call this point, well, to match the formula, I'm going to give it some generic numbers here. Notice the slope at DC. Okay, so let's call this point D comma C. Then the corresponding point on the inverse curve is C comma D. Remember that the graphs of inverse functions look like a mirror image of one another across the line y equals x. So this is the line y equals x. So again, they're just reflections across that line. So whatever the x coordinate was in the point DC becomes the corresponding y coordinate for the point that's reflected across the line y equals x on the inverse curve. Okay, so if we look at the derivatives, let's say here's the slope of the point DC on the function. So let's call this y equals f of x. And the other one let's call the inverse, although it's just a naming regime, right? It doesn't matter which one we call the inverse of the function. One thing to notice is that the tangent line for the corresponding point on the inverse curve, basically because we switched the x and the y coordinates, then when I think about slope being the change in y over the change in x, so for f, let's see, the slope is going to be change in y over change in x, generically speaking. Then the slope for f inverse is the change in x over the change in y, where x is referring to f of x graph. X and y are referring to the f of x graph. So hopefully that makes sense. That in other words, again, I'm not suggesting that the slope formula in general is change in x over change in y. I'm simply saying that the slope of the inverse curve is the change in x on f. So let me make this subscript maybe. The change in x on f over the change in y on f. So in other words, the slopes are reciprocals at corresponding points. So let's go up here and just give an example. Let's say this has slope, this function has slope, let's say, of 1/2. Then if that's the case, then the slope of the inverse function is going to be 2 over 1. So notice that they're both positive. It's not the negative reciprocal. We're not saying that they're perpendicular to each other. We're simply saying that because we swap the x's for the y's and vice versa, going from the original curve to the inverse curve, that the slopes, therefore, are going to be reciprocals of one another. So the inverse function theorem, if f is differentiable, strictly monotonic on an interval, and the derivative is not 0, then the inverse is differentiable at a corresponding point. And basically this is just saying in a theorem exactly what I said a moment ago about the graphs. So they're reciprocals of one another. Let me do this with an example in example 4 so that you start to get a feel for this. So we have this function, x to the 5th plus 5x minus 4 is the function. I want to prove, first of all, that it has an inverse. So prove inverse exists. And by the way, we have no chance of finding the inverse. You are welcome to try your little heart out. I don't want to squelch that effort. I can tell you that the end of the story is there's no way to find the inverse of this function analytically. So when I take the derivative, I'm going to get 5x to the 4th plus 5. Well, this is always positive because x to the 4th, an even power, regardless of what x is. X to the 4th has to be positive times 5, which is positive, or at least it has to be non-negative. And of course, adding 5 is positive. So altogether, this is strictly positive. It doesn't even have a 0 slope anywhere. So the slope is strictly positive, which means it's strictly, the function is strictly monotonically increasing. And if it's monotonically increasing, that means that it passes the horizontal line test. It passes the vertical line test because, which makes it a function. It also passes a horizontal line test because the slope, the curve never goes up and then comes back down. So the inverse exists, basically. That's what we know. The inverse exists. So now we're looking for the slope of the inverse curve at x equals 2. So let's write this in words. Slope of f inverse curve at x equals 2 is going to be equal, it's the same, as the slope of y equals f of x, where y equals 2. This is the point where students get stuck sometimes. They think they can just plug in the same x value. But remember that f of x and f inverse of x are reflected graphs of each other over the line y equals x. In other words, all of the xy pairs on the function are yx pairs on the inverse function. So I need to plug in y equals 2 into the original function. So I plug in y equals 2 to the original function, and I have to remember what the original function is. X to the 5th plus 5x minus 4. Now you might be thinking, well, this is going to be a bit of a bear to solve. You would be correct. If I add 4 to both sides, let's see, I'll get this. This isn't a normal way of solving a 5th degree polynomial. If you remember from your pre-calculus or college algebra course, solving a 5th degree polynomial, we can look at Descartes' rule of signs, we can do the rational root test, we can do all kinds of things to try to figure out how to factor this and find the zeros. However, in this case, because I know it's an invertible function, this is a really big key. Because I know it's an invertible function, if I guess, yes, I'm going to guess, if I guess the x value that gives me this y value of 2, then I'm guaranteed that that's the only x value that gives me that y value, and so I'm done. So I'm just going to look at this, 6 equals x to the 5th plus 5x, and I'm going to guess x equals 1, and check that it works. 6 equals, does it equal, 1 to the 5th plus 5 times 1? Yes. So that means f of x, that curve goes through the point, let's see, x equals 1, 2, which means the graph of the inverse function goes through the corresponding point of 2, 1, because it's reflected across the line y equals x, so I exchange the x and the y values. So when I ask for the slope, which is the derivative of the inverse function, at x equals 2, that's the same as the reciprocal of the slope of the original function at y equals 2, which means x equals 1. So process that for a moment. The inverse function slope at 2 is the same as the original function slope at 1. It's reciprocal.
Well, I don't know what the inverse, I can't get the inverse function, basically. The reason we're jumping through these hoops is because I can't get the inverse function, which means I don't have a function to just take the derivative of. But I can figure out what the derivative of the original function is. There it is. It's 5x to the fourth plus 5. So this is 5x to the fourth plus 5, because we were plugging in x equals 1. So this gives me 5 times 1 to the fourth is 5 plus 5 is 10. So there's our final answer. It's a little bit of details there to put this all together, but it's actually a really powerful and nice result. So in conclusion, the main point of this particular lesson is that inverse functions exist if the derivative of f of x is either always bigger than 0 or always less than or equal to 0. Inverse functions, f inverse, let's say. i.e., if f is monotonic, then f inverse exists. Ready for the next lesson.